Different types of linear programming problems. In this module, you will learn about different types of linear programming problems. We already know the definition of a linear programming problem and its related terms. A linear programming problem consists of a linear function to be maximized or minimized subjected to certain constraints in the form of linear equations or inequalities. Example, max z equals x plus y, subjected to x plus y minus 6 is less or equal to 0. 2x plus y minus 8 is less or equal to 0. X is greater than 0 and y is greater than 0. A linear programming problem consists of the following components: a set of decision variables, an objective function, a set of constraints. Objective function. It is a linear function z equals ax plus by, where a and b are constants, which has to be maximized or minimized. Here in the example, max z equals x plus y is an objective function. Decision variables. In the objective function, z equals ax plus by, x and y are decision variables. Here in the example, max z equals x plus y, x and y are decision variables. Constraints. The linear inequalities or restrictions on the variables of a linear programming problem are constraints. In the given example, x plus y minus 6 is less or equal to 0. 2x plus y minus 8 is less or equal to 0. X is greater than 0 and y is greater than 0 are the constraints. Different types of linear programming problems LPP are manufacturing problem, diet problem, transportation problem. A manufacturing problem deals with units to be manufactured or sold for maximum profits. Each product requires fixed manpower, machine hours, labor hour per unit, warehouse space, and maximize the profit. A diet problem deals with amount of different kinds of nutrients which should be included in a diet and minimize the cost of foods to be included in the diet. A transportation problem deals with a transportation schedule in order to find the cheapest way of transporting products from a company to the market and minimize the transportation cost. Let us look at a manufacturing problem. A furniture dealer deals in only two items, tables and chairs. He has 50,000 rupees to invest and a space to store 60 pieces. A table costs him 2,500 rupees and a chair for 500 rupees. He can sell a table at a profit of 250 rupees and a chair at a profit of 75 rupees. Assuming that he can sell all the items that he buys, how should he invest his money in order to maximize his profit? Step 1. Decision variables. Let x and y be the number of tables and chairs. Step 2. Objective function. Profit should be maximum. Profit for table is 250 rupees and profit for chair is 75 rupees. The equation becomes maximize z equals 250 into x plus 75 into y. Step 3. Constraints. Total money to invest is 50,000 rupees. Cost of one table is 2,500 rupees and that of a chair is 500 rupees. The equation is 2,500 into x plus 500 into y less or equal to 50,000. Space is for 60 pieces. X plus y less or equal to 60. The LPP becomes maximize z equals 250 into x plus 75 into y subject to 2,500 into x plus 500 into y less or equal to 50,000. x plus y less or equal to 60, x greater or equal to 0, y greater or equal to 0. The graph for the LPP is given below. The closed figure formed by points O, A, B, C constitutes the feasible region. The optimal solution exists at the vertices of the polygon. Applying corner point method, we get optimal solution is 10, 50. Maximum profit is 6,250 rupees when the dealer buys 10 tables and 50 chairs. Now let us consider the diet problem. 1 kilogram of food X is 16 rupees and 1 kilogram of food Y costs 20 rupees. Find the least cost of the mixture which will produce the required diet. Solution. Step 1. Decision variables. Let X kilogram of food X and Y kilogram of food Y be mixed. Step 2. Objective function. Cost should be minimum. Cost of food X is 16 rupees and cost for food Y is 20 rupees. The equation becomes minimize Z equals 16X plus 20Y. Step 3. Constraints. The following table shows the formulation of the equations for constraint. The LPP will be minimize Z equals 16X plus 20Y, subjected to X plus 2Y greater or equal 10, 2X plus 2Y greater or equal 12, 3X plus Y greater or equal 8, X greater or equal 0, Y greater or equal 0. It gives an unbounded feasible region. The optimal solution will be at the vertices A, E, G, F. Applying corner point method, we get. Hence, the minimum cost is 112 rupees when 2 kilograms of food X and 4 kilograms of food Y is mixed. Lastly, let us look at a transportation problem. A catering agency has 2 kitchens to prepare food at 2 places, A and B. From these places, midday meal is to be supplied to 3 different schools situated at PQR. The monthly requirements of the schools are respectively 40, 40 and 50 food packets. A packet contains lunch for 1,000 students. Preparing the capacity of kitchen A and B are 60 and 70 packets per month, respectively. The transportation cost per packet for the kitchen to schools is given below. How many packets from each kitchen should be transported so that the cost of transportation is minimum? Also find the minimum cost. Let X be the food packets transported from kitchen A and Y be the food packets transported from kitchen B to schools P and Q. Then 60 XY food packets will be transported to school R. X greater or equal 0, Y greater or equal 0 and 60 minus X minus Y greater or equal to 0. X greater or equal 0, Y greater or equal 0, X plus Y less or equal to 60. 40 minus X greater or equal 0, 40 minus Y greater or equal 0, X minus Y minus 10 greater or equal 0. Total transportation cost Z is given by Z equals 5 into X plus 4 into Y plus 4 into 40 minus X within brackets plus 2 into 40 minus Y. This results in Z equals 3 into X plus 4 into Y plus 270. The LPP is given by minimize Z equals 3 into X plus 4 into Y plus 270, subjected to X plus Y less or equal to 60, X less or equal 40, Y less or equal 40, X plus Y greater or equal to 10, XY greater or equal to 0. The graph for the above is the feasible region is the shaded region which is bounded. Applying the corner point method, we have minimum cost is 300 rupees at the point 1, 10, 0. From kitchen A, 10 packets, 0 packets and 50 packets to school P, Q and R respectively. From kitchen B, 30 packets, 40 packets and 0 packets to schools P, Q and R respectively. In this module, we have learnt about different types of linear programming problems.